Welcome to a Fluidit demonstration. Here, I'll show you how to set up and run flood simulations. But before jumping to the software, let's review a few details. Storm focuses on an easy configuration and run fast. This will certainly save you time and allow interesting applications such as real-time or large-scale modeling. Storm has two simulators, the well-known Stormwater Management Model as the 1D engine and CA Flood as the two-dimensional flood simulator. Both engines can be used separately or simultaneously. Here, I will use both engines to show you three different approaches. First, a scenario where only the 2D engine is used for flood analysis. Second, using results from a 1D model as input for the 2D domain. And for the third scenario, let's explore a coupled simulation when both engines work simultaneously. Let's first see how to set up 2D-only simulations. We will start by adding the elevation and precipitation data to the model. Both will be used as input for our simulation. First, right-click on the DEM Manager header to add elevation data. Here I will choose a basic elevation DEM, which allows public available data to be fetched on the fly directly from the software. Most of these have global coverage. It's also possible to create your own connections via WebMap tile service. You can create DEMs from a locally stored raster file or even from vector data such as point, contours, or land XML. All these features give flexibility for the user to combine elevation data from multiple sources in order to achieve the best representation of the elevation in the area. Simply drag layers above to indicate they have precedence, or even double-click to deactivate some layers. Each scenario will remember the group of DEMs active. In cases when the resultant elevation still needs adjustments, simply use the DEM modification tool to modify the elevations directly in the software. You can create multiple DEM modification layers to achieve your goals. Alright, let's now talk about precipitation. There are several ways to add precipitation data. You can import your own, download historical data directly from the software, or use a tool to generate synthetic storms, as I will do right now by selecting some parameters to define duration, amount, and I will also choose a pattern. Now let's add a rain gauge component. So this component will work as a link between the precipitation data and other components in the model. Now this model has ground elevation and precipitation data. I will then delineate a flood model area. You could easily import this area too. This area will represent our 2D domain borders. Now select the flood model area to access its properties. Then choose simulation type as 2D only and include a water source, in this case our rainfall. Notice that these simple steps were the main settings for our scenario, but you can also define here other parameters that will control the flood simulation, such as the cell size, get buildings directly from OpenStreetMap, and other CA flood settings. To run the simulation, simply right-click on the area and choose to simulate surface flow. You can follow the simulation progress from the bar below. Notice it is also possible to have multiple and independent flood model areas in the same scenario. This flood domain has an area of about 100 hectares. We are now using a 1 square meter cell size. This equals to about 1 million computational cells. For a 3 hours simulation period, the runtime is under 30 seconds on my laptop, as you can see. It always depends on the hardware, but this can give you an idea of how fast simulations can run in Storm. Once the simulation is completed, you can manage how the results are displayed using the flood result background layer and highly flexible built-in visualization tools. This saves you time from post-processing and visualizing results in an external software. There are several result types readily available such as depth, velocity, flood hazard, and flow direction. Here I will choose a distinct color scheme for the maximum water depth result. Many other components can be used to set up your scenario. For instance, it is possible to define spatially varying parameters such as hydraulic roughness or infiltration for different areas. In this scenario, I've also modified the DEM and added 2D culverts to refine the model setup. Now let's check the second approach. Here we will first run a 1D simulation where the nodes are overflowing, and this overflow time series will then be used directly as input for the 2D flood simulations. To achieve the proposed, first go to the menu bar and run the 1D simulation. Now let's choose the manual as the simulation type in the flood model area and enable nodes overflows as inputs for the 2D domain. It's possible to use many sources at the same time. Here we can see some nodes overflowing. Again, right-click to run the 2D simulation. Notice that in this scenario, most of the hydrological processes and hydraulics in the drainage network are modeled using the 1D components of the swim engine. This approach is handy, especially when you already have drainage system model of your area and simply want to start exploring the flow paths when overflows happen. Using a similar setup, you could also leverage the 1D engine to handle the hydrology and hydraulics upstream, generating then the necessary input for your downstream flood analysis. Now let's have a look at the third approach when both engines work simultaneously. For that, let's assume that only part of the earlier scenario will be running a coupled simulation, and the rest will remain a 1D only model. Notice that I have removed the catchments in this area so that precipitation will be directly applied to the flood model area as a rain on the grid approach. Differently than in the previous scenario, the runoff will now be calculated entirely by the 2D engine. The runoff then enters the 1D network to finally be drained downstream. To achieve this, let's first make sure that the simulation type is set to fully coupled. Running the simulation now starts both engines. In this scenario, I have also chosen the nodes that will be coupled. This means that the nodes, in this case, are the components interconnecting the 1D and 2D engines. You can choose the orifice equation or discharge rating curves to define how water flows in and out stormwater inlets. Here's an example of a small area within our larger fully coupled scenario. You can observe how the road network acts as floodways and how the inlets do their best to capture the surface flows. In the end, the inlets drain the remaining puddles of water. This example animation is achieved using Storm's powerful built-in schematic editor. This allows modelers to craft visual dashboards using various types of time-sensitive maps and figures to effectively communicate the modeling results and analysis. All results as time series, raster files, or GIS data can also be easily exported for use in other software. However, there are multiple ways to visualize and analyze these results directly in Storm, reducing the need for other post-processing tools. But we will discuss more about this in another video. Before we wrap up, let's summarize some highlights of the flood simulation features. Integrated DEMs. Users can merge multiple sources, modify elevations on the fly, and also bring in buildings with a click. Flexibility when preparing your model. You can use a rain on the grid approach or swim hydrology, and even both in some cases. Spatially varying parameters, multiple flood model domains at once, model different scenarios, compare them, and even use statistical analysis for the results, and finally the versatile options discussed in this video. The fast 2D only simulation type that can already include culverts, our special intermediary approach where overflows from the 1D network feed the 2D flood simulations, and the fully coupled approach for a more detailed analysis. To learn more about how to use our fast flood modeling methods to save you time in the next project, please get in touch with us, book a live demo, and start your free trial period. Thanks for watching and happy modeling!